Alrighty, y'all. Today we're taking a look at question 8 for homework 2. And for this one, we're trying to find the change in the electric potential, or our delta V, for this whole mass. So we're starting with an infinite wire right here with a given lambda, our given length charge density. And we're trying to find the change in the electric potential. So if we look at our equation for our delta V, right? It's just our equation for potential energy, but with the Q divided out, with that extra charge divided out. So it'll be from R1 to R2, the electric field dotted with dr, right? So if we're looking at electric field, we're going to be using, and this, since it's just the wire, it's going to have cylindrical symmetry. So that's going to give us, since we're using the Gaussian surface, cylindrical symmetry, all that mess, electric field is going to equal lambda over 2 pi epsilon naught r. And what a fun coincidence that this is only giving us the magnitude of that electric field. But if we draw in our Gaussian surface, right, over here, and we have a second one that's 1 centimeter away, or we'll say, and we'll draw another one 2 centimeters away. I'm just going to use another Gaussian surface for the exact same thing, right? The direction of our electric field is going to be going out perpendicularly to that wire. Now radius is also going that way. The angle between them is going to be 0. Cosine of 0 is 1. So when we're dotting the two vectors together, it's going to be the magnitude times 1. This is the cosine of the angle between them, right? So we can just multiply by the magnitudes here. So if I simplify that, it's going to be our delta V equals negative integral from R1 to R2 of our lambda over 2 pi epsilon naught R dr. And that's the equation that we're going to be using for the rest of this now. So obviously this is just going to spit out our answer once we plug everything in and solve it all out. But we got to plug in things the right way. So our R1, the radius that we're starting at this 1 centimeter, but we're keeping everything in meters to keep consistent units. So that's going to give us our negative integral from 0.01 meters to where we're ending with that 2 centimeters, 0.02 meters. And our lambda is also given, which is 1 nanocoulomb per meter. And since we're keeping our units consistent, that's going to be 10 to the negative 9th coulombs per meter. All over 2 pi epsilon naught r dr, right? So all this mess, we can see we have a constant, a constant, a constant, and a constant. So we're going to pull all of that out of our integral, which is going to give us negative 10 to the negative 9th over 2 pi epsilon naught times the integral from 0.01, 0.02, and that would have just been 1 over r. So I'm just going to rewrite that as r to the negative 1. No, actually I'm not. I'm going to write it as 1 over r. Why the hecky heck not? So now we have the integral of 1 over r dr. That's just going to end up being the natural log of r evaluated from 0.01 to 0.02. So we plug that back in, all the way back in. That's going to give us our negative 10th to the negative 9th over 2 pi epsilon naught times ln of 0.02 minus ln of 0.01. And that is technically going to give us an answer. I'm just going to also take this negative and just distribute it in here to make it better on my brain. 10 to the negative 9th over 2 pi epsilon naught times, since I'm distributing, I'm just going to also just flip the order of these. So that's going to be ln of 0.01 minus ln of 0.02. And if you solve all of this out, that's going to give you your final answer. And but we're going to plug that into our calculator using our epsilon naught equals 8.85 times 10 to the negative 12. And of course, pi, you can just use the pi button, or you can use that it's 3.14159267939841979058209741058209749459, or something like that. I think I rounded in there somewhere. But anyways, you're going to plug all that into your calculator, and that's going to give you your answer, because that's just the integral solving for that delta V. All right, well, thank you very much for watching. I hope you found this at least a little bit helpful. Let me know if you have any more questions about this problem or any other problems. If there's any other questions that you want me to solve, just let me know, and I will do my best to explain them, because I guess Sydney explains stuff.